Dudes, let's kind of get this show on the road here. Today, last day of content for the semester. Yeah, right? New stuff ends after today, so that's good news. I talked to second hour about this test 7 date, and the consensus there was that next week was better than this week. So we'll plan on the test 7 then Tuesday of next week. Format for this, I have 3 parting gifts for you. Partner. Each partner can bring in a sheet of notes, front and back, and open book. Yeah, like you can take a textbook and use it. How's that sound? Calculator throughout, 4 things. Okay. We'll figure that out. I think we have an odd number of people in this section, so there's going to be at least one group of 3, so there'll probably be some kind of random draw for that. But I would say yes-ish, mostly yes. We'll sort. I haven't figured out the exact test format and everything yet, but since it's next week, I'm not in a rush to hammer out those details. We'll have them by Friday for sure. And we'll talk about it then. Sound good? Everybody happy with that? I'd also make mention that you guys all have the option to retake a previous test or double a high test score. If you think you are in a retake, situation, we'll worry about that after test 7 is in the book. So if you're kind of contemplating that, kind of think on that, and I'll start collecting a list of people that are looking to do a retake, and we'll worry about that then in the week and a half or whatever we have following that test 7. Sound good? So the other 2 days this week, we'll do a little bit of test 7 review stuff, and then start some AP specific review, do some specific AP practice stuff. And kind of get going on that. Sound good to you guys? In those 4 classes or whatever, 5 classes following test 7, just be doing AP specific targeted review. So whether it's like, hey, these are the specific topics I feel bad about, can we do a little reteach on those and do some examples and talk about how I'm supposed to, what I need to remember from this topic or whatever, or just do practice things and do the review kind of organically as it comes up, doing practice problems. We'll figure that out as we go, based on what you guys feel like you need. Okie doke. All right. So today we're going to look at, I have one type of problem from 9-1 that I want to talk about because we haven't talked about this, and this is something that I've seen pop up, especially as a multiple choice question on an AP exam. And if you're not familiar with what to do with this, it can be a little bit time consuming if you're not looking at it the right way. Same idea from 9-4. Again, we'll look at a specific type of problem, and there's a little bit of a formula shortcut through some specific types of differential equations. We'll talk about that and how you can use that to take a 10-minute problem and turn it into a 30-second problem, which again is just a time saver for a multiple choice situation on an AP exam. And then we'll look at 7-3, which is trigonometric substitution. And that's that'll be the most of our day will be spent doing that, which is just another integration technique. Everybody cool? All right, let's hit it. So the thing that I want to talk about here today is from 9.1 is this type of problem. So you're given a solution to a differential equation, y equals yada, 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 and the original differential equation, y prime equals yada, yada, yada. Now, to confirm that y is a solution to y prime, you can either take y and differentiate it to get y prime, or you can take y prime and integrate it to get y. Which route is probably going to be the easier of the two? Differentiation or integration? Differentiation should be the answer there. Mostly because there are integrals that I can give you that look like things you should be able to do that are impossible using any of the methods you have available to you, and really are impossible using non-numeric methods. So like you'd have to do some kind of approximation, numerical approximation to do it anyway. Not the case for derivatives. Anything that I could reasonably give you is something you can be able to differentiate by hand. Now, the catch here is that if I look at the two equations, if I look at y is in terms of t's, but if I look at y prime, that's in terms of y's, right? So I'm probably going to have to do a little bit of messing around with both of these to get to check that one is actually the solution for the other. So let's start with taking the derivative of y. So y is written as 1 plus c e to the t over 1 minus c e to the t. If I want to do the derivative of that, what do I need to use? Quotient rule. The quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Everybody feel good? I'm going to now distribute things through in the numerator. I'm going to leave the denominator untouched though. Oops, that's a negative there, right? Oops-a-daisy. And when I do that, I notice some nice things happen. When I combine like terms, those guys cancel out. And then the other two terms in the numerator are like terms, so I can just add those together. So here's the value of y prime in terms of t, right? What I'm going to do next, if I want, is compare that to the y prime that's given. The only problem is the y prime that's given is in terms of y instead of t, right? That's a hassle. But since we know what y is, we can just drop that in place and then try to do some simplifying. Everybody okay with what I just did there? If I look at this piece right here, I notice that it's going to have the denominator that I need, right? It's going to have 1 minus c e to the t squared. So I'm not going to FOIL the denominator out, but I am going to FOIL the numerator. Everybody okay? Now I'm going to make a common denominator between the minus 1 and the other fraction. That common denominator is going to be 1 minus c e to the t squared. I'm going to leave the denominator in that factored form, but I'm going to FOIL out the numerator. So when I do that, oops. Let's distribute through that negative sign then. And when I do that and combine some like terms, some nice stuff happens. So those guys all cancel out. And the remaining stuff is like termed, so I can just combine those. And then that will reduce. And lo and behold, looky. They are the same. Now, this is a particularly nasty example because of the fraction involved for y. Let's do another example that's maybe not quite as nasty as this one. But this would be a common presentation, or I would say not uncommon presentation for a multiple choice question where we're going to give you, where we could give you the differential equation and ask which one of these is a solution, where you can just differentiate and check, or you could give the solution and ask which one of these would have been the differential equation that it started, which again, you can just differentiate to check. Would be the route you'd want to go. But let's look at another example before we move on to the next thing. So here it says, show that y equals 2/3 e to the x plus 2 e to the negative 2x is a solution to the differential equation y prime plus 2y equals 2 e to the x. So again, we'll start the same way by taking the derivative of the solution. Any questions as to how I got that derivative? Everybody see the chain rule that I had to do to differentiate the e to the negative 2x? Okay, so that's that. Now, all I'm going to do is take that differential equation that's given and plug the y back in. And thankfully, we don't have a bunch of fractions and stuff to go on, so this is quite a bit simpler. Distribute the 2 through. Oops, that's not 2x, it's 2e to the x out there. Okay. And now to just get the y prime by itself, I'm going to subtract the 4/3 e to the x over. So 2 minus 4/3 is 2/3. And I'll just subtract this guy over, because he's not a like term, he doesn't get combined. And we see that that is the same as what we got when we took the derivative. That one's quite a bit simpler to kind of get your way through, just because the algebra is not as nasty, because you don't have like, the y isn't a fraction, right? That makes life quite a bit simpler algebraically. And this is more in line of the level of problem that would run into like a multiple choice AP problem than the previous one, which is just kind of like an algebraic pain in the tuchus, right? We'll test the same level of understanding in much less time having to sort through this one as opposed to the previous one. Is everybody okay there? Okay. On to 9.4. So in 9.4, we want to talk about two specific types of differential equations. So if we have a differential equation in this form, like dy dt is equal to k times y, any differential equation in this form, its solution is going to be the initial value times e to the kt. That's the takeaway. So we had a bunch of algebra that we used to like show you why this is the formula that falls out. That's not important. What we want to be able to do is on an AP setting, if you notice your differential equation is in this form, right? If it looks like this guy, you can go straight to the solution without having to muck around through the algebra. This is just taking a 5 or 10 minute problem and turning it into a 30-second problem by recognizing the situation. Okay? Enormous time saver. So let's look at, do I have an example? I have probably an example down there somewhere. A similar situation would be if your differential equation looks like this. This is a BC situation though, just as an FYI. That wouldn't show up as a question on your exam. But if I recognize something like that, I can go straight to this solution. So if I have a differential equation in that form, oops, thought that looked wrong, P over M. We can go straight to this guy as our solution. Everybody's okay? And that's the takeaway. Okay, so this is just like, if you have a differential equation that looks like this is the formula, how to plug the numbers in, and we're not going to do this. We're not going to try to solve these differential equations. In particular, this one is a lot to algebra your way through. Like the algebra is not a whole lot of fun. It's still separable. You can still do it without having to do an integrating factor, but I wouldn't want to have to do it. I'd rather recognize that like, oh, that's logistic. Let me just take it and put it into the logistic form. So let's see here. Do I have a... I guess I didn't have one over here. Let's just write one real quick. So if we have the differential equation dp dt equals 1.05k and p of 0 is 10, I can immediately go to oops, that should be p, sorry, not k. And go immediately to the solution and I'm done. Right, the initial amount is the constant out front, the k is the factor on the exponent, and we're done. That's the takeaway from this. It's just like, this is the shortcut. We're not going to worry about the algebra in between. You could do it if you wanted to. It's not terrible, but like in terms of an AP exam, to do well, you got to be able to go fast. This is an example of some place where like, here's a 5-minute problem you can do in 30 seconds if you look at it the right way. Everybody's okay? Similarly, if we look at this example down here, I notice that my differential equation is in that logistic form. So I see that, okay, well, my K is 0.8. My M is 1,000. And my P naught is 100. So A is going to be M minus P naught divided by P naught. So that's 9. So P of T then is going to be M, which is 1,000, over 1 plus A, which is 9, e to the negative k, which is 0.8 t. And we're done. If you know what you're looking at, and you recognize it as, oh, this is just the logistic, I just have to plug in, P naught, M, and K into my formula, and there she spits out. And this is like a 10 or 15 minute problem to algebra it through, especially when you're not expecting that what you have to do that I did in 10 seconds, right? 30 seconds, something. That's the point. Is everybody okay? You guys should do some practice on this, so I'm going to assign 1 through 11 odd. That's like, I don't know, 5, 6 problems, something like that. Again, use the formulas to generate your solutions. Don't solve the differential equation by hand. If it asks you to draw a slope field, don't bother with the slope field, just skip that question. Everybody's okay? What I want to spend the bulk of our time talking about today is integration using trigonometric substitution. This is a BC topic, just as a heads up, but it will be something that will be on test 7 for sure. So we're going to spend some time doing this. It'll be something that you'll be expected to do in your Calc 2 class. So again, we're going to spend some time working on this. Yes. So the test 7 will contain chapter 9 and then these 3 sections from chapter 7, integration by parts, improper integrals, and then this trigonometric substitution. Does that feel okay? And again, next class or whatever, I'll spell out exactly the kinds of stuff that you'll have on your test so you can make sure you're prepared or whatever. And if we don't get to it on Wednesday, I'll definitely have it for you on Friday. Cool? Again, fair questions to ask for sure. Okay, so the first thing you'd want to ask is, okay, what do I need to look at in the problem to cue myself that this is the technique I need to do this integration problem? What should I be looking for in my integrals that would tell me that, hey, trig substitution is what you should be doing here? So what you'd want to be looking for is you want to look for square roots of a squared minus u squared, or a squared plus u squared, or u squared minus a squared. If you have the square root of any of those 3 things, that's your cue, where u is like some function. It might just be x, but it could be like x plus 1, right? Or it could be like 2 minus x squared or something, like you could have all kinds of stuff in there, right? Okay. To do this, we're going to be taking advantage of our Pythagorean identities. That'll be part of the algebra that we're going to be needing to do here. I rewrote your 4 Pythagorean identities in the form that you'd probably want them written in. If you don't remember them, I'm assuming everybody remembers that, like, sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared. But we're probably 50-50 on secant squared is 1 plus tangent squared, and cosecant squared is 1 plus cotangent squared. I'm sure you come up with them pretty quickly, like algebraing with the Pythagorean identity, but sometimes it's nice to have it just consolidated for me. All right. So let's go and show you the general idea. What I'm going to want to do is I'm going to want to find a way to algebra through a clever substitution this problem to get rid of the square root. That's my goal. So we're going to make a substitution. So I'm going to just replace x with an a times sine theta. And we'll talk about how to choose what to do for your substitution in a moment. I just want to show you that why this is going to work for us. Because this is the algebra that we're going to like kind of hand wave our way through once we get a feel for like, oh, this is what the substitution is going to do every time. I don't really need to write it all out every single time. I can just write down the substitution I'm making and then the simplified version afterwards and kind of spare myself a lot of stuff. So we're going to do it once here in good detail and kind of explain how it's going to work, and then it'll work this way every single time afterwards. So I've replaced the x with a sine theta, and then a sine theta squared is going to be a squared minus, a sine theta squared is a squared sine squared theta. And then I can factor out a greatest common factor. Is everybody okay there? And then 1 minus sine squared, I recognize, hey, that's cosine squared. And if I take the absolute value, or if I square root that, since they're both squared, that's just going to give me the absolute value of a cosine theta. Is everybody okay with that? So this substitution, again, what this is accomplishing, it's allowing me to cancel out that radical. Right? That's the entire purpose of what we're trying to do here. Which now we can, ideally, would be able to integrate this without having to do, a second substitution or whatever, right? Yes, sir. So, yeah, that's a great question. What am I going to do about the absolute value? We're going to take care of it here by just choosing sine over a specific interval of theta so that the cosine has to be positive when it comes out. So we're going to collect all this information here into a table in a moment and show you how we're going to do this to make sure that the absolute value is what we want. So for this, we would just be like, if I just choose theta to be between negative pi over 2 and positive pi over 2, it just becomes a cosine theta. I feel okay? Which is great. A is a constant, so it doesn't matter if we absolute value that. The problem is the absolute value on the variable, which was the theta in this case. So that's all we're going to do. Sound good? All right, let's collect this together now. Because the big question is why pick sine theta here? Why not cosine theta or, tangent theta or cotangent theta or one of these other things? And this is the idea. So when we are in the form a squared minus x squared, we're going to pick a sine theta. And we're going to assume that the theta is between negative pi over 2 and positive pi over 2. And then if it's a squared plus x squared, we're going to say x is a tangent theta. Again, from negative pi over 2 to positive pi over 2, guaranteeing us a positive tangent coming out, and so on and so forth. Is everybody okay? All right. So from here on out, we're just going to do some examples because there's still some like detail that needs to be resolved here, but it's best done inside of some specific example. So it can show you how this series of substitutions we're going to make and then unsubstituting how that's going to have to work. Okay? So we have our problem. First thing I'd want to look is to make sure that I can't solve this just doing a simple U substitution. Take a look. Are you convinced? When I see that the degree of the polynomial underneath the radical is not like one more than the degree of the polynomial outside the radical, right away I'm going to be like, okay, I'm not going to be able to U sub my way through that. Is everybody okay with that? Now, if it is one more, you're not guaranteed to be able to get away with just U subbing it, but if it's not, the U sub is off the table to begin with. Right? If the stuff under the radical has degree one more than the stuff outside, you might be able to, but you still have to check, because if the stuff outside the radical's in the denominator, it won't work. You know, like depends on where it's at. Okay? So if I look at this one, I'm looking at this piece. Looks like we're in that form, right? Everybody agree? Okay, so we're going to make this substitution. What are we going to pick for x then? What is a? 3 sine theta. So if I do that, we have this, right? Everybody good with the substitution? But we have a problem. Who sees the problem? It's subtle. What variable are we integrating with respect to? X. But what's the variable in our function? Theta. Is that okay? No, we need that to match. So somehow we're going to have to replace dx with a d theta. How do we do that? You just differentiate that equation with respect to theta. So now this guy I can substitute in. Is everybody okay with what we've done so far? Okay. Now I'm going to do that simplification under the radical, right? Does that to there, right? Is everybody cool with the substitution or the simplifying that I'm doing? Okay. We're not going to write it next time. We're just going to do the simplification on the next step and call it good. Everybody happy? There's some simplification we can do there. Brings us down to that. Cosine squared over sine. Well, first of all, is that integrate? Can we integrate that? No, right? A u sub's not going to work. We don't have the right stuff to make that work. So let's try some trig identity stuff to get us to a place where maybe we can do it, integrate it. So cosine squared over sine squared is expectation that you would know this and be able to rattle this off right away. Cotangent squared. Again, if you're soft on that, those trig identities, like you need to have those. Okay. Do we have an antiderivative formula for cotangent squared? No, right? The antiderivative of cotangent times cosecant is, what is that? It's cotangent, right? Or I'm sorry, it's cosecant. And the antiderivative of cosecant squared is cotangent. But we don't have anything for cotangent squared, right? So I'm going to use that other Pythagorean identity. Back up here and show it. So cotangent squared is cosecant squared minus 1. Everybody okay there? So I'm just going to rearrange that. And I want to do that because I know I have an antiderivative formula for cosecant squared. Oops, not cosine, cosecant. All right, what's the antiderivative of cosecant squared? Negative cotangent. And the antiderivative of 1 is theta, and then we have a plus c. Is that our final answer? No, unfortunately not. There's a problem with this answer. Who sees it? It's subtle. What's that? Yeah, excellent. So Anthony notes that the beginning problem we integrated with respect to x, but we have an answer in terms of theta. All right. So how am I going to translate these thetas back into x's? I'm going to use this. So if I divide both sides by 3, I know that sine theta is equal to x over 3. Everybody cool with that? That means if I build myself a right triangle with acute angle theta, the opposite side needs to be x, and the hypotenuse needs to be 3. And then this other side, if we call it y, I know that x squared plus y squared has to equal 3 squared. So y has to be the square root of 9 minus x. Sorry, 9 minus x squared. Everybody's okay there? Okay. So in our problem, we have cotangent theta. Cotangent is adjacent over opposite. Everybody's okay there? So that'll take care of that piece. How am I going to get the theta, though? I'm going to take this piece. How do I get theta by itself? How do I get theta by itself there? Just do sine inverse to both sides, right? Everybody's okay there? So that's what we'll drop in. And now we have an equation in terms of x. Is that okay? We're going to do a couple more examples of this because this process is not easy the first time you're kind of going through it. This is going to feel like a stretch, and that's okay. That's normal. But once you kind of get the feel for it, it's like, okay, yeah, these are kind of all the same. It's not that big of a deal. The hardest part is the back substitution at the end to get your variable back in terms of the correct variable. So again, really important that while you're doing this, like that when you're writing your sines and cosines and stuff, that you're not dropping the variable there. I see some of us still have a tendency to write, like, instead of sine theta, just write sine and no variable afterward. Here, that's really going to come and bite you in the buns because the variable name is really important to getting the correct answer because you have to back substitute potentially through 3 layers of variables. Here we just had 2. We went from theta back to x. You might have a situation where you go x to u to theta, or x to theta to u, and you have to like step through multiple layers of substitutions. So it's really important you're keeping the variable name on the trig pieces. Very common mistake that comes up and bites you guys. All right, let's go ahead and do another example. So here we have the integral of 1 over x squared times square root x squared plus 4. Again, first step would be to check to see if you can just u sub this thing away. Can we do that? No, right? It should be pretty easy to look at that and go, that ain't gonna fly. So what are we gonna do? You can always write, if it was like 6 there or something, you could just write square root 6 squared, so a is the square root of 6. That's fine, no big deal. So you can always just take, doesn't have to be a doesn't have to be an integer, it could be an irrational number, and that's okay. Is that, okay. So if we look at this one, here, we're gonna be in this form, right? So we're going to want to be using a tan theta as our substitution. And then we're going to need dx then is going to be 2 secant squared theta d theta. Everybody okay? What's that going to simplify down to? Can we see it without having to algebra it? It's okay if you say no. What? Nope. It's going to be 2 secant theta. You guys see it now? Kate still says no. So I factor the 4 out, right, to get to here. And then tan squared theta plus 1 is secant squared. That's one of our Pythagoreans that I gave you guys at the beginning that I'm like, I know you guys probably don't remember that, but you'll need these guys frequently, so I rewrote them all for you. So that gave me the secant squared, and then we square root it because it's all under the square root and just becomes 2 secant theta. Is that cool? Yeah. Okay. And again, if the algebra is like, ooh, you did a lot there, I don't see it, that's okay. You can ask to see it again, and I don't mind doing it again, but it's one of those where just like, what if you did the square root first? What do you mean? So you're saying you want to take the square root of this thing? Yeah. What's it give you? No. So like, so that's not true. You can't distribute a radical across addition or subtraction, right? You can break a radical at multiplication or division, but not at addition or subtraction. And it should be easy to see if I just said like, this is A is 1 and B is 4, then you'd be saying that, oh, this should be equal to 3, but the square root of 5 is definitely not 3, right? Is that what you're saying to do? Okay. So good question. That's a very common mistake for students to make, is get confused on when I can break that radical and when I can't. So I'm glad you brought it up. But definitely can't break radicals at addition and subtraction. And because you can't do that, we have to do what I did. Does that feel good? Everybody else feel okay? Who here thinks that you would have made that mistake had Anthony not asked about it? Yeah, right? Like very common. Absolutely. Go ahead. Okay. Are we ready to pick up where we had left off after our digressions? I don't mind taking those. What should we do here? I'd be doing some reducing at this point, right? Pull the 1/4 out front, I guess. Okay. Worth checking, can I integrate this as it's currently written? I have to do some kind of U substitution. Is that going to work? My choices for U could be secant, but the derivative of secant is secant times tangent, so that doesn't give me enough. Or I could pick tangent as my U. If I did that, the derivative of tangent is secant squared. Well, that won't work. I don't have enough to do that. Or my other option for you might be tangent squared, and the derivative of that is definitely not secant. So no is the answer. I can't integrate this as it's currently written. So I think at this point, probably what I would want to try is to do some kind of trigonometric rearrangement to see if I can get this into something that's more appealing. I'm going to probably want to do this by writing things in terms of sine and cosine, would be my suspicion. So secant is 1 over cosine. And then 1 over tangent squared is the same thing as cotangent squared, which is cosine squared over sine squared. Now can I do a u substitution to integrate this? Yeah, I should. My u I want to pick would just be sine theta. So du is going to be cosine theta d theta. Everybody feel okay with what I did there? I'm going to think about this just as u to the negative 2 then. What's the antiderivative of u to the negative 2? Negative 1 u to the negative 1? Everybody's okay there. What's the problem? My answer needs to be in terms of x. How many substitutions did I make in this problem? 2, right? I went from x to theta and then theta to u. Everybody's okay there? So to go back, I'm going to have to go u to theta and then theta back to x. Everybody's good with the plan? So I know that u, let's pick a new color, is equal to sine theta. So I'm going to have 1/4. Well, let's write it this way. Negative 1/4. Let's write it. Negative 1/4 sine theta plus c. Is everybody okay there? U to the negative 1 is 1 over u. And since u is sine theta, I just have 1 over sine theta. Multiply it to the 1/4, I have 1 over 4 sine theta. I guess there's a negative on there too. Everybody's okay? All right. Then I need to go back and look at my theta. So I know that tan theta is equal to x over 2. So if I draw a right triangle with theta as an acute angle, tangent is opposite over adjacent. So when I use the Pythagorean theorem, the third side is 4 plus x, or the square root of 4 plus x squared. Everybody okay with that? And in my problem that I'm trying to deal with, I have a sine theta in there. So using this right triangle, sine is opposite over hypotenuse. So that's what I need. And I'm going to go and plug that back into here. And I'm going to have negative 1/4. And because the sign is in the denominator, I'm going to flippy flop them. And that ought to do me. Is everybody okay there? That was hard, right? We do another. Just keep practicing on this because, again, like, you need to see this a couple of times to feel like you got the hang of this, and you're going to have to spend a little bit of time working through these because, like, I don't know, I assigned you guys 7 or 8 of these. The first couple are going to take a long time to get through for you, and that's normal. By the end, they should be going, you know, spending half the time for the last one as you did for the first one, even though it's a more difficult problem, just because you've gotten used to the procedure, which is really the same kind of throughout. The hardest part is the back substitution at the end. All right, let's look at the next one. So here we have the integral of x over x squared plus 4. First thing you should do is check to see if you can do this without a trigonometric substitution. Can we do this one without a trigonometric substitution? I notice the degree under the radical is 2 for the polynomial, and the degree outside the radical is 1. So there's a chance that a u sub will work on this, right? Let's try it and see if it'll go, because if it does, boy howdy, I'd rather do that than have to trigonometric substitution. And if I just divide by 2, that's going to give me the part that I need. Oops. Everybody's okay there? Is that doable? You better believe it. I'm going to think about that as u to the negative 1/2. So I'm going to pull the 1/2 out from the du, and then I'm going to have u to the 1/2 over 1/2 plus c. So those just kind of cancel out. So I'm going to have the square root of x squared plus 4 plus c. And we're all done. Does everybody feel okay with what we did there? So again, I just included this to show you that just because there's a square root of something squared plus something squared doesn't mean it has to be a trigonometric substitution, right? Could just be a regular old u sub problem that, thank goodness, it was just a regular u sub. That makes my life so much simpler. Thank you very much. I'm glad to avoid the trigonometric substitution because I'd prefer not to do it if I don't have to. Okay, let's look at this next bad boy. Oh, brother. Look at that denominator there. Is that in one of the 3 forms that we had at the beginning? No, right? Not as it currently looks, but could I put it into one of those forms? The answer is going to be yes, but what is the tool that I'm going to use to do that? The tool is completing the square. Let's show you guys how I'm going to go about doing that. So this is my thing under the radical. That's what I'm going to complete the square with. I'm going to factor out that negative from the variables. Now, if I look at x squared plus 2x, what's the constant part that I need to complete the square there? X squared plus 2x plus what is a perfect square? 1, right? X squared plus 2x plus 1 is 1 plus x squared, right? So what I'll do is I'll just we'll add a 1 and subtract a 1 right after, which is like doing nothing at all, because we just added 0, no problem doing that. I'm now going to distribute the negative just to that very last term that I don't need. So I can kick it out of there. Is everybody okay with what I did there? And now I notice that I have 4 minus x plus 1 squared. Ooh, Mr. Kulik, that was nasty. Yeah, but now that you've seen it happen, you're like, okay, you know, if I run into a weird-looking denominator, like a polynomial that's not written as a perfect square, oh, I know I just have to complete the square and it should turn into what I need. Well, that stinks to tack that extra step on there, but like I can handle it. I just would rather not have to, but it is what it is. Is everybody okay with this? All right. So if I look at this piece right here, I go up to my chart. That looks like this one, right? 4 minus x plus 1 squared. So I need x to be 2 times x plus 1. Or, I'm sorry. Sorry, I need to make a u substitution here first. My apologies. Oops, and that's an x up top. We got to make a u substitution before I get to that. Let's do that. I got carried away. So u is going to be x plus 1. So du is just dx. But I have this x up here. So x is going to be u minus 1, right? There we go. And now we'll do that substitution for this thing. So I'm going to say u is going to be 2 sine theta. So du is going to be 2 cosine theta d theta. Is everybody okay with the substitutions that I made here? Still doing okay? Notice that this time we went from x to u to theta, as opposed to the previous problem where it went x to theta to u. So just a different order of the substitutions. But that matters in terms of like putting it back together. We got to follow the reverse order back out of this. If I look at that denominator, the square root of 4 minus 4 sine squared theta, what is that going to simplify down to? What is that going to simplify down to? Can we see it? 2 cosine theta, right? Do you see it? Again, once you do a couple of these, it becomes more and more easy, or easier and easier to see those simplifications. You don't have to write out the step every single time. If you're not there, write out the steps. Okay? We're going to talk through some of them here because this is example number 3 or 4 where we've done this same simplification. And I'm trying to stretch you a little bit. If you're not ready to be stretched when it gets to be on your own time, though, like, don't feel like you need to. Write it out if you need to. Do a little bit of simplification. And, oh, yeah, look what happened. That's great. What's the antiderivative of 2 sine? Negative 2 cosine theta. And then the antiderivative of 1 is theta. Everybody feels good? Okay. The problem is, what variable do we need this in terms of? X. So remember, we went x to u to theta. So we're going to have to go from theta back to u and then u back to x. All right, so I know u is 2 sine theta. So I know sine theta is u over 2. If I build my right triangle with theta as my base angle, opposite over hypotenuse because it's sine, my other side is going to be square root of 4 squared minus u squared. And in my problem, I have cosine. So cosine theta is adjacent over opposite. Everybody's okay there? And the other piece I need is a theta. So if I do the sine inverse of both sides here, I know that theta is sine inverse of u over 2. Everybody's okay there? Now I got to go from u to x. So if I go back and I look here, we said that u is equal to x plus 1. Oh, let's just cancel those guys. And we're done. What did you guys think there? This was a stretch. That's okay. I recognize that it's not easy the first time looking at this. Okay? We did 3 examples. Hopefully, as we went through, you started to get the feel for what you need to do. The hardest part is recognizing, like, when do I need to make a U substitution? When do I need to make a trigonometric substitution? Once you start to feel good on that, and you're able to backtrack your way back to x's, you'll find that these problems all kind of become the same. Okay. So your assignment from this section is just 5 through 19 odds. So I think we had 1 through 11 odd from 9-4, and then 5 to 19 odd from 7-3, and that's going to be your last homework assignment. I might assign some review problems or whatever as homework points or whatever, but like your last textbook homework assignment for the semester. How's that feel? Right? Feels good to feel like we're starting to put some stuff to bed here. I imagine some of your classes can go right down to the nitty-gritty. So again, the plan for the rest of the week, we'll do a little bit of Test 7 review stuff and a little bit of AP review on Wednesday and Friday. We'll have your Test 7 will be in class on Tuesday, barring some weird schedule happening on Tuesday, which I hope is not the case. But I haven't looked that far ahead. I guess I could do that. All right, here, folks, then.